Hello, welcome to this lesson in the Linear Algebra Tutor. Here we're going to learn how to take the inverse of matrices that are larger than 2 by 2 matrices. Now, the technique we're going to use here is very, very powerful, very common. You can apply it to matrices of any size, including 2 by 2s. Typically, what we learned in the last section to calculate a 2 by 2 matrix inverse is kind of the cut and dry way that we teach introductory students to take inverses because it's bulletproof and it's easy. What we're going to do here is learn how to use row reduction techniques in order to calculate the inverse of a 3 by 3 matrix, but you can apply it to 4 by 4s and 5 by 5s. You can even apply it to 2 by 2 if you want. But the point is we're going to use this method to find the inverse, and then we'll check our work and make sure that we're getting the right answer. So in this case, the matrix that we have is 1, 1, 1, negative 1, 3, 2, 2, 1, 1. This is our matrix, and we would like to find the inverse of this matrix. Now, there probably are techniques out there, you could probably go off and look. I know that you could go and look and find a mathematical formula, like we did for the 2 by 2 to calculate the 3 by 3. But then what are you going to do when you get to 4 by 4 and 5 by 5 and 6 by 6? You're going to have formulas for everything. It's just going to get cumbersome. So what we're going to do is apply row reduction techniques to be able to find the inverse of this matrix that's extensible to matrices of different size. And the way you do it is you set it up as follows. You set up an augmented matrix. You write the matrix that you're given on the left, 1, 1, 1, negative 1, 3, 2, 2, 1, 1. You put your dotted line here, all right? And then on the right-hand side, you put an identity matrix. So you're putting 1s along the diagonal and 0s everywhere else. Effectively, what you're trying to do is you're trying to find the inverse such that when you multiply the inverse matrix times this one, you're getting this on the right. So what we do is we set up our matrix with the augmented matrix with what we're given on the left and what we're trying to get to on the right. So let's use row reduction techniques to attempt to make the left-hand side of this augmented matrix look like an identity matrix. And when we get there, whatever has happened to the right-hand side is what the inverse is. That's the technique. So I'll say it one more time. We're trying to manipulate the left-hand side. We're doing row reduction techniques on the whole thing, but we're trying to make the left-hand side look like the right-hand side currently looks, like an identity matrix. Once we've achieved that, then whatever has happened to the right-hand side, by definition, is the inverse of the original matrix. All right, so let's go through it. And we've done this process enough with equations that you should be fairly comfortable with it. First thing is we want to put a 1 up here, and we already have that. So let's leave the top row alone. 1, 0, 0, like this. We want to make this guy 0 and this guy 0. So to make this guy 0, I'm just going to add row number 1 to row number 2. So row 1 plus row 2, like this. When I add this together, I'm going to get 0. When I add these together, I'll get 4. When I add these together, I'll get 3. When I add these together, I'll get 1. When I add these together, I'll get 1. When I add these together, I'll get 0. Just like that. Now, I also want to put a 0 down here, which is underneath in this first column. So I'll multiply this row by negative 2 and add. So negative 2 times row 1 plus row 3. Multiply this by negative 2 and add, I'll get a 0. Multiply by this by negative 2 will give me a negative 2 and add, that'll give me a negative 1. Multiply by this by negative 2 and add, that'll give me a negative 1. Multiply by this by negative 2 and add, that'll give me a negative 2. Multiply by this by negative 2 and add gives me 0. Multiply by this by negative 2 and add, that gives me 1. So you see, as I start manipulating the left-hand side, the right-hand side is beginning to change the way that it looks. So once I can get the left-hand side into an identity matrix with 1s along the diagonal and 0s everywhere else, the right-hand side will be the inverse that I'm seeking. That's basically what we're doing here. All right, and so what I'm going to do now is go on to the next step. And what I typically want to do next is make the center element a 1. So I'll keep the top intact. So what I see here is that I want to put a 1 in this location. Now I could just take this row and multiply it by 1/4. That would put a 1 here. But it would also introduce a fraction here, a fraction here, and a fraction here. And if you can avoid getting fractions in your matrix, it's going to be helpful to you because carrying fractions everywhere is a real pain. So I'm trying to look for an alternate way other than putting a fraction there. And I see that I can multiply this row by 3 and add it to this. That would also put a 1 in this location without screwing up anything I've done over here. So it'll be 3 times row 3 plus row 2. So take this multiply by 3 and add it, gives me 0. Take this multiply by 3, that gives me negative 3, and add it, gives me a 1. Multiply by this by 3 and add it, that gives me a 0. Multiply this by 3 and add it, that gives me negative 6. And I go and add it to that, I get negative 5. Multiply this by 3 and add it, gives me 1. Multiply this by 3 and add it, gives me a 3 right here. And now I just want to carry the bottom along for the ride. Now I'm starting to make real progress because I have 1s along the diagonal, although this is still a negative 1. I have 0s in nice locations. I have lots of 1s everywhere. So I know it's just a matter of time before I can get everything down to the place that I want to get it to. So the next thing I want to do now that I've got a 1 here is I want to try to figure out a way to put a 0 here. So what I want to do is keep the top row 1, 1, 1, 1, 0, 0. And I'm going to keep the middle row 0, 1, 0, negative 5, 1, 3. But I want a 0 under here. So I'm just going to add this row to the next row. So it'll be row 2 plus row 3, like this. And this plus this gives me 0, this plus this gives me 0, this plus this gives me negative 1, this plus this gives me negative 7, this plus this gives me 1, this plus this gives me 4. So you see the right-hand side is starting to significantly change its form. Now I can start seeing the end game. I have a negative 1 here. I'm going to make it into a positive 1 simply by multiplying this last row by negative 1. So let me copy this matrix up here so we don't lose continuity here. Let me just copy it. I'm not going to do any manipulations yet. I have 1, 1, 1, and I have 1, 0, 0, and then I have 0, 1, 0, and then I have negative 5, 1, 3, and then I have 0, 0, negative 1, and then I have negative 7, 1, 4. All right, and what I want to do is I want to, first of all, there's a couple of things I can do. I'm going to leave the center row here intact. That's not going to change at all. So I'm going to have 0, 1, 0, negative 5, 1, 3. That's not changing at all. But on the bottom row, what I want to do is on the bottom row down here, I want to multiply this by negative R3. All I'm doing is multiplying by a scalar, negative 1 times R3. These stay unchanged. This becomes a 1, this becomes a 7, negative 1, negative 4. So I just multiply the bottom row by negative 1. That gets my nice diagonal elements here. And in the same step, I'm going to multiply this guy times negative 1 and add it to this. So I'm going to say negative R2 plus R1. When I take negative row 2 and add it here, I'm going to get a 1. Negative multiplied here gives me negative 1, and I add it, I get a 0. This, when I multiply and add, I get a 1. When I multiply this by negative 1 and add it, that'll be 5 plus 1 gives me 6. Multiply this by negative 1 and add it gives me negative 1. Multiply this by negative 1 and add it gives me negative 3. 6, negative 1, negative 3 on the right-hand side. So now the matrix is almost exactly where I want it, but I want to put a 0 here. So I just go down here and perform one last step where what I'm going to basically do is take row 3, negative of row 3, and add it to row 1. So I take negative of this and add it, I get a 1. Negative of this and add it, I get a 0. Negative of this and add it, I get a 0. Negative of this and add it, so that's negative 7 plus 6 is negative 1. Negative of this and add it is going to give me 1 plus negative 1 is 0. And then negative of this and add it is going to give me 4 minus 3 is 1. And everything else remains the same. 0, 1, 0, negative 5, 1, 3, 0, 0, 1, 7, negative 1, negative 4. So through a bunch of steps, basically what we have figured out is that when we manipulate row operations, we can get the left-hand side to be an identity matrix with 1s on the diagonal, 0s everywhere else. And the right-hand side is what we're now going to call our inverse matrix. So the inverse of the matrix is negative 1, 0, 1, negative 5, 1, 3, 7, negative 1, 4. That is the inverse matrix. Now don't forget, what is the point of an inverse matrix? The point of an inverse matrix is it's a matrix such that you multiply it by the original matrix and you get an identity matrix back. So let's really quickly check that because I think that that's useful. It's a useful skill to have. And many times you'll be asked to verify it anyway. So it doesn't matter the order in which we multiply it. So let's write our inverse down first. Our inverse is -1, 0, 1, -5, 1, 3, 7, -1, 4. That's our inverse matrix. We multiply it by the original matrix. The original matrix that we were given is given way on the board by this matrix here. So I'm going to write that one down as 1, 1, 1, -1, 3, 2, 2, 1, 1, like this. So I need to multiply that out. All right. Now, when it's a 2 by 2 matrix, you can get away with kind of adding and multiplying in your head, but when it's a 3 by 3 matrix and above, it gets hard, especially with negative numbers, to do the row multiplications and additions without writing anything down. So the way I recommend doing it is just put an equal sign below, and let's say we're going to go and work it out the long way. So over and down. So what I'm going to have is -1 times 1 is going to give me -1. 0 times this is going to give me 0. And then 1 times this is going to give me 2. So see, I've gone over and down. When I sum this up, it's going to be the first element that I have. All right? Now let's go down this way and this way. -5 times 1 is -5. 1 times -1 is -1. 3 times 2 is 6. All right? Then we have 7 times 1 is 7. -1 times -1 is 1. 4 times 2 is 8. So those are the first three elements in the first column. Now let's go to the next column. This times this. So -1 times 1 is -1. 0 times 3 is 0. 1 times 1 is 1. And then we'll go down like this. We'll say -5 times this is -5. 1 times 3 is 3. 3 times 1 is 3. So we're going over and down. Now let's go over and down again. 7 times 1 is 7. -1 times 3 is -3. So we'll do it as -3. And then 4 times 1 is 4. So that gives us the second column. And then finally we'll do the third column over and down. -1 times this gives me -1. 0 times 2 gives me 0. 1 times 1 gives me 1. Close my matrix off. Go down like this. -5 times 1, -5. 1 times 2 is 2. 3 times 1 is 3. And then finally 7 times 1 is 7. -1 times 2 is -2. 4 times 1 is 4. So that's it. Let's hope that we did not make any mathematical errors. It's very, very, very easy to do. So if I've made any here on the board, I'll just correct them as I go. But hopefully we've done the right thing. So what we have is -1 plus 2, so we get a 1 here. -1 plus 1 is 0. -1 plus 1 is 0. Here we have -5 plus -1 is -6, plus 6 is 0. Here we have -5 plus 6 gives me a 1. Here we have -5 plus 5 gives me a 0. Here we have 7 plus 1 is 8, plus 8 is 16. Clearly that's wrong. Let's go back up here and look and make sure I didn't make a mistake. 7 times 1 is 7. -1 times this gives me +1. 4 times 2 would give me 8. Clearly there's no way that that's going to give me 0 here, so I know I've done something wrong. I've checked it twice. I go back over here and I look to my inverse. I have a 4 here, but then I noticed that I was being a doofus here. When I wrote down my inverse, I was just going a little bit too fast. I actually have a -4 here, so let's double check. -1, 0, 1, -5, 1, 3, 7, -1, -4. It just goes to show you that no matter how much you practice this stuff, simple mistakes can happen. In this case, I accidentally forgot to write a negative down there, which ends up carrying through when I verify my inverse, that should be a -4. And so that whenever I get down to it, I'm going to have some wrong answers here. So let's go and make sure that they're right. So let's go over and down right here. 7 times 1 is 7. -1 times this is 1. -4 times 2 is -8. And now whenever I add this together, I get a 0, as I suspect that I should. All right? But I'm going to have the same sort of problem whenever I calculated this entry and this entry. Let's do it again for this guy here. Over and down. 7 times 1 is 7. Negative 1 times 3 is negative 3. Negative 4 times 1 now is going to give me a negative 4. Same exact thing over here. 7 times 1 is 7. Negative 1 times 2 is negative 2. Negative 4 times 1 is negative 4, like that. And whenever I go back through and add these together, 7 minus 7 gives me a 0, and 7 minus 6 here gives me a 1. And now I verified, it's not a bad idea anyway, if you have time on a test to verify your inverse is correct. You could, of course, do it with a calculator, a modern calculator, but it's a nice idea to check it. And the way you check it is by taking the inverse, multiplying by the matrix, and you should always get an identity matrix back. So I'll revise my answer and say this is the inverse. This is what you would circle on the test. I got the correct answer up here in the work, but just forgot to bring the negative sign down there. Now, we have done this process just for one example, and I know that it's hard to generalize based on one example, but the same concept holds. If you're going to go and try to do this with a 4x4 matrix, then what you're going to aim for is an identity matrix that looks like this. Right? So you would set up an augmented matrix where on the left you had your matrix and on the right you had this, and you would try to make the left-hand side look like this identity matrix. If you had a 5x5, you would have an extra 1 on the diagonal and zeros everywhere else. And of course you could go to 2x2 and try to make it look like this and calculate the inverse that way. But for 2x2 matrices, typically we use what we did in the last section because it's a little more direct and row operations, and you get the answer kind of like that. But for anything above 2x2, you're going to need to do these sorts of row operations to calculate the inverse. So I hope you've enjoyed this lesson. Make sure you understand the concept. I really do highly recommend that you check your work at every step here. You notice how I carried a sign incorrectly. Luckily, it happened in the answer. If I carried a sign incorrectly up here, then I would have rippled through the entire thing, and then you have to go erase everything as you go, and it's just a pain. So make sure you know how to calculate the inverse here, and that the property of the inverse, multiplying by the original matrix, gives you that identity matrix. That's going to come very, very handy in the very next section where we learn what inverses are really used for. So follow me on to the next section. We'll talk about why we use these things called matrix inverses in linear algebra.